Okay, so let's start. Uh, in the previous class, I introduced the class of Reed-Solomon codes, and we studied some of their properties. So the Reed-Solomon codes are those codes with the parity checkmate. So this is the so-called generalized Reed-Solomon codes. These have parity check matrix of the form 1 power 1 power 1 square power 1 power n minus k minus 1 1 2 alpha 2 square up to alpha 2 power n minus k minus 1 so on 1 alpha n square n raised to n minus 1 times another matrix. It's a diagonal matrix, so the form v1 v2 up to n, right? Where alpha 1 alpha 2 up to alpha n are distinct and v1 v2 up to n are all non-zero. Right, so the VIs need not be all distinct, but they have to be non-zero, otherwise it doesn't make sense. It's as though you're removing some of the coordinates. So recall that the alpha 1, alpha 2 up to alpha n were called the code locators, and the VIs were called the column multipliers. A nice property of course, so we saw that Reed-Solomon codes are MDS, but also another nice property of Reed-Solomon codes is that the generator matrix also has the same form. So that is also equal to this times some other column multiplier matrix, but it has exactly the same set of code locators. So the generator matrix of the Reed-Solomon code is exactly of the same. Of course, one of the main differences is this is a k by n matrix. 1, 1, k minus 1, and these column multipliers could be different. So this is what we saw in the last class. We saw a proof of this particular statement, and towards the end we were talking about conventional Reed-Solomon code. So the usefulness or utility of showing that the generalized Reed-Solomon codes have this generator matrix is that now essentially the encoding process is evaluating a certain polynomial at n different. So you have the message polynomial m of x, which is m0 plus m1x so on plus mk x to the k minus 1. So this is the message polynomial, and the code word is basically equal to m of alpha 1, m of alpha 2 on m of. So the code word is obtained by evaluating the message polynomial at n different points. But of course, naturally, we saw that one big disadvantage of the generalized Reed-Solomon codes is that you need a large enough alphabet size. So Q has to be at least n. right? Otherwise, this doesn't work because all the alpha i's have to be distinct, correct? So this is sort of the polynomial interpretation of generalized Reed-Solomon codes. Then towards the end, we also discussed conventional Reed-Solomon code. Right? So these are codes wherein these are generalized Reed-Solomon codes obtained by taking alpha I or alpha j to be equal to alpha raised to j minus 1 and b j to be some alpha raised to b times j minus 1. Right? Where alpha has of course you can't choose an arbitrary alpha from the field. You need to make sure that all the alpha j's are distinct. So you need to make sure that alpha power 0, alpha power 1, alpha square up to n minus 1. So all of these are distinct. So if you look at the cyclic group which is generated by alpha, this has to have size at least n. Right? Okay. So now let's look at the parity check matrix corresponding to a conventional Reed-Solomon code. So this is equal to so we start with 1 alpha power 0, 1, 1, 1 alpha square to alpha power k minus 1 alpha square of power 4 2 times k minus 1 cube k minus goes on up to alpha n minus 1 to alpha power k minus 1 times alpha power b, sorry, 0. So this is 1 alpha power b alpha the 2b alpha n minus 1. I'm just using this. So Bj is alpha raised to b times j minus 1. Alpha j is equal to alpha raised to j minus j going from 1. Okay. So let's try to see what this looks like. So the first column is obviously going to be all ones. What is the second column going to look like? It is all of these entries are multiplied with alpha raised to b. So it's going to be alpha to the b, alpha to the b plus 1, alpha raised to 2b plus 2, or alpha raised to 2 in b plus 1. Third entry is going to be alpha to the 3b times alpha cube, right? So that is alpha raised to 3 into b plus 1 and so on. So it's going to be alpha raised to, it's going to go all the way up to alpha raised to k minus 1 b plus 1. So what about the third column? I have 1 alpha square alpha to the 4 and so on times so this is alpha. Sorry, n minus k, correct. So the third row is going to be alpha raised to b plus 2, so on all the way up to b plus n minus k minus 1. Right? So probably the easier way is to think about it in the following way. Let us look at the ijth entry. Ith row jth column. This is going to be the ijth entry of this particular matrix times the jth entry of this particular, right? What is the ijth entry of this particular matrix? So it is alpha j raised to I minus 1. Okay, so if you look at this here. So the so the jth entry has powers of alpha j, and the ith row has something raised to I minus 1. The first row has raised to 0, second row is raised to 1. Okay, this times alpha. So what is the jth entry in this? So it is alpha raised to b times j minus 1. But what is alpha j? Alpha j is alpha raised to j minus 1. This is alpha raised to j minus 1 times I minus 1 times alpha raised to b times j minus 1, which is nothing but alpha raised to I minus 1 times b plus j minus 1. Okay. So this is a general expression for the ijth entry of the parity check matrix of the Reed-Solomon. Now, what does every code word have to satisfy? So every code word must satisfy uh, a minus 1 times b plus. Okay, so you have, this is, in other words, you can write this as alpha raised to b plus I minus 1 whole raised to j minus 1. So if you look at C1, C2 up to Cn, so C times this should be equal to 0. The code word times the parity check matrix times the code word should be equal to 0 for it to be a valid code. Or for every row, every I, we want summation j equal to 1 to Cj 1 whole raised to j minus 1 should be equal to 0. So in other words, so this should hold for all I. So So I varies from 1 up to n. Right? So if you view this as a polynomial, if you take c of x to be c1 plus c2x plus c3x square and so on to en to the n minus 1, then what this is saying is that for it to be a valid code word, we must have c of alpha to the b equal to 0, c of alpha to the b plus 1 should be equal to 0, c of alpha raised to b plus what? N minus 1. So for every row, this should hold. So it's n minus k minus 1. This should be true. Right? All right. So this is true, right? So what does this mean? It means that all of these, alpha to the b plus 1, all the way up to alpha to the b plus n minus k plus 1, are all roots of this code word polynomial. So this implies that alpha to the b, alpha to the b plus 1, alpha to the b plus n minus k minus 1 are roots of c of x. Right? So if you look at any polynomial of degree n minus 1, it is a valid code word if and only if all of these are roots of the polynomial. It's an if and only if statement. So C is a code word if and only if alpha to the b plus 1, so on all the way up to alpha to the b plus n minus k minus 1 are roots of the code word polynomial of C of x. So if these are roots, then what can you say about C of x? So if you consider the polynomial x minus alpha to the b, x minus alpha to the b plus 1, product of all of these up to x minus alpha raised to b plus n minus k minus 1. What can you say about this respect to C of x? Yeah, it's divisible, right? So the product of all of these should divide C of x. Correct? So what can you say about this particular quantity over here? What kind of a polynomial is it? What is the degree? N minus k. It's a degree n minus k. And every polynomial which is divisible by this and has degree less than or equal to n minus less than or equal to n, okay? Sorry, less than or equal to n minus 1 is corresponds to a valid code word polynomial. Yeah. So if you consider any polynomial of degree n minus 1 less than or equal to n minus 1 and which is divisible by this, it is a valid code word. It corresponds to a valid code word. And vice versa. If C is a valid code word, then it has to be divisible by this. Right? C of X has to be divisible by this. So it is possible to generate all code words, right, by multiplying this with some other polynomial. So if I take this polynomial, multiply it with any polynomial of degree less than or equal to k, sorry, strictly less than k, then I get a valid code word. So that, sorry, exactly. So that's why strictly less than k. It can be n minus. So the coefficient could be 0, right? The coefficient of x power n minus 1 could be 0. That's a polynomial of degree less than n minus 1. So if I look x minus alpha raised to b 1 x alpha b plus n minus k minus 1 times, say, some m prime of x degree less than or equal to k minus 1. So this gives you all possible code words. Right? So another way of encoding Reed-Solomon codes. So remember, we looked at one view of Reed-Solomon codes, which was as evaluations of the message polynomial at n different points. Right? So one view of generalized Reed-Solomon codes is that the code word is obtained by evaluating a certain polynomial m0 plus m1x k1 to the k minus 1 at different points, alpha 1, 2 up to alpha n. The code word can be viewed as evaluation of a certain polynomial at n different points. Now, what does this tell us? If you look at Reed-Solomon codes, not generalized Reed-Solomon codes, so conventional Reed-Solomon codes, the code word is in fact obtained by multiplying this particular polynomial with some other message polynomial. So the message polynomial over here and the message polynomial over here are not necessarily the same. Okay, but nevertheless, you can obtain every code word by multiplying, by just doing polynomial multiplication. You don't even have to evaluate. So another view of conventional Reed-Solomon codes is the following. So you can view the code word itself as a polynomial, and that is equal to whatever, some message polynomial times some other polynomial p of x, where p of x is exactly equal to this. So this is another characterization of conventional Reed-Solomon code. Just using the theory of polynomials, we've got very different views of the same set of codes. And depending on the application, one particular way of looking at it may be helpful, another way might not be. In fact, the decoding of generalized Reed-Solomon codes can also be viewed in terms of polynomials. Maybe I won't do it right now, may take it up at a later point of time. But for all of these Reed-Solomon codes and so on, they have their roots in the theory of polynomials. All right. So now we have constructed Reed-Solomon codes, but the problem is that they require very large field sizes. So can we do something about this? Can we obtain codes of smaller field sizes? So one approach is to look at subcodes of Reed-Solomon codes. So we know that Reed-Solomon codes are good, right? So now we know how to construct good codes over very large field sizes. Just take a Reed-Solomon code that's going to be maximum distance separable. So that's the best possible minimum distance you can hope for a given rate. Right? But now if I look at, but now suppose I want codes over the binary field. Currently, I have no way of constructing a good code of large minimum distance over the binary field. If I take higher order fields, I know how to construct. But for small field sizes, what do you do? One way is to look at subcodes of Reed-Solomon codes. So I construct a code over a field of size 2 to the power m, where m is sufficiently large, right? And then I list all possible code words. I pick only those code words which are valid binary code words, so which only have zeros and ones, no other field elements. So that's a subcode of generalized Reed-Solomon. So it's a subfield subcode of the Reed-Solomon. I'm picking a subcode where all the elements comes from a subfield of the original Reed-Solomon. Turns out that the binary subfield subcode of the generalized Reed-Solomon code, this has a special name. It's called the BCH code because it was developed separately even before Reed-Solomon codes independently. But BCH codes are special cases of Reed-Solomon codes, which are special cases of generalized Reed-Solomon. So these subfield subcodes, they have a special name. They're called alternate codes. Of generalized Reed-Solomon code. So what is the general approach? Suppose you want to construct a code. So we want a good code over FP. Okay, where P is, it may be prime, it may not be prime, whatever. P is assumed to be small, much smaller than N. P is strictly less than N. So what do we do? You choose an M. A good code is one which has, for a given rate, it has a large minimum distance. That's what I mean by good code. So large rate, large minimum distance. So you choose an M, which is such that P to the power M is greater than N. Okay, I construct the Reed-Solomon code. So let's see the generalized Reed-Solomon code constructed over F P to the M. Right? So that's a code. Some construct the generalized Reed-Solomon code, but now the entries are going to be from FP to the M. But what do I know about FP to the M? I know that FP is a subfield of FP2. I define a new code C prime to be the set of all code words in the generalized Reed-Solomon codes such that all the entries come from this base field. Okay, so I started with the base field, which has small size. I then look at some extension field whose size is greater than my block length. I construct the generalized Reed-Solomon code over this extension field, and now I'm only picking those code words for which all the entries come from the base field. So this is clearly a code in FP. So this lives in FP. That is obvious. But now the question is this a linear code? And what can you say about the rate? What can you say about the minimum distance? Right? So firstly, is this a linear code? Okay, correct. So the sum is two code words. So it's a group code. But why do you say it's a linear code? So clearly, the set of all code words over here forms a group. Yes, you agree it's a group code, right? That the sum of every two code words is a valid code word. That is fine. Sum or difference of any two code words is going to be a valid code. It's going to lie within C prime. Take two code words in C prime, add them up, or subtract them, and still lie within C prime. So that is true, but it is not absolutely not clear that if I take linear combinations, I'd still lie within C prime. Not, I don't know if it's a linear code or not. But it turns out that this is indeed a linear code. Right? So let's think about why this is true. Okay. So now let us look at H. So suppose that H is HGRS is the parity check matrix for the code C, the generalized Reed-Solomon code constructed over FP to the M. Right? Now, in general, each element Hij is going to be in FP to the M. But what do I know about FP to the M? So FP to the M, P to the M is an extension field of FP. And a nice property of extension fields is that they form vector spaces over FP. Okay, let that sink in for a moment. So, okay, so this is what we want to prove. This is what we want to prove. So I have another sub result. It says that if FP is a subfield of FQ, then FQ forms a vector space over FP. For this, of course, I need to prove that all the properties of vector spaces are satisfied. So clearly, FQ forms a group anyhow, so there's no issue over there. The only thing you really need to show, if you think about it, is that linear combinations of elements in FQ should be closed under all linear combinations, and that is true because FQ is a subfield of is an extension field over FP. Any linear combination of elements from FQ with coefficients from FP also lie within FQ because elements of FP are also in FQ. So this is now you should make sure, convince yourself that all the properties are indeed, but maybe I'll just leave that as a homework. The proof of this particular line. But fine. FQ forms a vector space over FP. So if I take FP to the M, then this forms a vector space over FP. What will be the dimension of this vector space? The dimension. How many elements are there in FP to the M? Are there in FP to the M? P to the M. How many elements are there in FP? So what should the dimension be? Mention. Think about it in another way. Yeah? Just guess. Okay. How did we construct finite field? FP to the M from FP. Or what is one way to construct FP to the M from? Give an irreducible polynomial. Look at the set of residues modulo that irreducible polynomial. Right? So what did the elements of the field of the big field look like? Okay, what is the degree that you should look at? What is the degree of the irreducible polynomial? If I want to construct FP to the M. M. So all elements can be viewed as polynomials of degree less than or equal to M minus 1. Right? So now can you use this to answer the question? So you have the set of all polynomials, degree less than or equal to M minus coefficients from FP. Does this form a vector space? And if so, what is the dimension of this vector space? what is the dimension of this vector space? Set of all A0 plus A1x, where A0, A1 come. A0 plus A1x. A0 and A1 come from some field. This forms a vector space. We all agree with that. So now, can you find a basis for this vector space? Okay. So what do you want? You want a basis which is two vectors v1 and v2. What are vectors in this case? Polynomials. We want two polynomials such that I can write every polynomial as v1, whatever, alpha 1 v1 plus alpha 2 v2, for which alpha 1 and alpha 2 are elements of the field. Can you find a basis? 1 and x forms a basis. So I can write every element over here as a0 times 1 plus a1 times x for a1, a0 and a1 from the field. What is the dimension? Okay, come back to this. Dimension is n, right? This forms a vector space of dimension . Basically, all you need is some set of polynomials which forms a basis. And the most trivial set of polynomials you can think of are the monomials. Right? Monomial of degree 0, monomial of degree 1 is 1x, x square up to x. So that forms a basis. They're all linearly independent. Okay. So now fp to the m forms a vector space of dimension m over fp. Right? What does this mean? This means that I can write, well, one way of representing the vector space is in terms of whatever the exact structure, polynomials. But any vectors, any finite dimensional vector space can be written in terms of matrices. Right? So I can view, if I just look at the set fp to the m over fp as a vector space, I can represent every element as a tuple, right, as an m tuple. In this case, the m tuple would be the coefficients of 1x, x square up to xm minus 1. Now I could start with a different basis. I could consider some other set of independent polynomials, linearly independent polynomials, and still arrive at the same solution. So for example, in this case, I could have, of course, one way to choose is 1 and x. That forms a basis for this vector space. But I could also equally choose 1 plus x and x. These two are linearly independent. But now this gives me a different basis. So once I fix a basis, I can represent every element of this vector space as a tuple. which is the coefficients of the basis vector, alpha 0, alpha 1. So as long as I fix a particular basis, every element alpha in fp to the m can be written as a vector. Alpha, so this underline means that it's a vector with all the entries coming from fp. fp whole raised to m. Okay? So remember, when I'm doing this, I'm not at all considering the multiplicative structure of fp to the m, this field. Right? Only thing I care about is addition within fp to the m and linear combinations with coefficients taken from fp. I really don't care about how other elements of fp to the m multiply. That is why I can write it as fp whole raised to the m, because this in itself is not a field. Right? So these two have the same vector space structure over fp, but they don't have the same field structure. Multiplication here, multiplication between two arbitrary elements of this set is not defined. Okay. So now I know that every element can be written as a vector with coefficients from fp. Let me go back to this. I have the parity check matrix. I can write every element of the parity check matrix as a vector now. Correct? So hij can now be written in terms of a vector. But of course, for this I need to specify some particular basis. So I can write hij, each is now a vector. So this is equal to omega hij, vector hij, where this omega essentially corresponds to the basis. This is the representation or the coefficients hij with respect to the basis omega. So for example, if you wanted to think of this as a polynomial, if you look at the vector space of polynomials, then I could write this as a0 plus a1x can be written as 1x times a0 a1. That's one way to write. And now I can essentially just work with a0 and a1 as long as I'm only considering operations with respect to f. So now what do I know? I know that C, for C to lie within C prime, remember all of these entries come from fp. This happens only if C is in fp to the n and h c is equal to 0. Transpose is equal to 0. But what does this say? This is summation all I, summation j equal to 1 to n, hij should be equal to 0. So this is the set of all vectors C in fp to the n such that this now I can write hij again in terms of my basis. So again I have the same basis for the entire fp to the m, summation j equal to 1 to n, omega hij Cj should be equal to the zero vector Fp. So C is a code word. So any C in Fp to the n is a code word if and only if this holds for all I. Correct? But now this is essentially irrelevant. You can pick any basis. So in other words, with respect to some particular basis, summation j equal to 1 to n h, remember this is a vector, hij, cj should be equal to the zero vector. So now each constraint over fp to the m now essentially translates to m different constraints on cj. Remember that this is a vector. So there's hij of 1, hij of 2, all the way up to hij of n. Write this as summation j equal to n hi1 j of 2 up to hij of m times j equal to 0, which is the same as saying, again, this is multiplied element wise. So for all I and for all, let's say L, so I goes from 1 to n minus k, L goes from 1 to m, summation j equal to 1 to n hij of L ej should be equal. And this, all of these operations are over fp. So I started with parity check matrix over fp to the m. Now I end up with a new parity check matrix, but now over fp. But the number of checks have now increased. Correct? So for every parity check I had over fp to the m, I get m different parity checks over fp. L K L m. This is true. So some of these parity checks may not be independent. Not claiming that all of these parity checks are independent, but the number of parity checks that I can get is n minus k times m. So number of independent parity checks is at most n minus k into m. See to that? Okay. Now what happens to the minimum distance? So okay, so before that, so since this is the number of independent parity checks, what can you say about the dimension? So what can you say about dimension of C prime? So remember, K is the dimension of the original code C, right? So what is the dimension of this? It is n minus the number of independent parity checks which is greater than or equal to n minus k times. Could be larger, but it's at least this amount. I can guarantee that the rate is no smaller than this. Okay, but what about the minimum distance? N minus. I don't know if this new code is MDS. Original code was MDS. The new code need not be MDS at all. But with respect to the old code, what can you say about the minimum distance of the new code? Is it always larger, smaller, could be anything? Again, interpret it in terms of the minimum Hamming weight. The original code was a linear code. The new code is also a linear code. So the original code, what was the minimum Hamming weight? N minus k plus. Okay. For the new code, what happens to the minimum Hamming weight? Can it decrease? Yeah. So I'm looking at a subcode of the old code. Right? So it cannot decrease, right? Because every code word in the new code has to be a code word in the old code. So it cannot have Hamming weight less than the minimum Hamming weight of the original code. That cannot change. Therefore, this is greater than or equal to, potentially it could increase. The minimum distance could increase, but it's definitely no smaller. So this is d min of C, but what was d min of C equal to? It was n minus k plus 1. So this is n minus k plus 1, right? So now if you want to think about it in terms of the dimension, so n minus k plus 1. So let's suppose that we designed this originally for some distance capital D, d equal n minus k plus 1. Then the dimension of the new code we know is greater than or equal to, so n minus k is basically capital D minus 1. So it is n minus D minus 1. So if I call this k prime is n minus D minus 1 times, or n minus dm. So if m equal to 1, then basically I recover MDS. So this is not MDS in general, because I know that the minimum distance is at least d, but now potentially the minimum distance could be but now potentially minimum distance could be larger than d, and the rate could be, it's at least equal. So we don't have a tight bound depending on how you choose FP and so on, and depending on how you choose the original generalized Reed-Solomon code, you could end up with different codes. We don't have a closed form expression for it, but these are some guarantees that we can. For any alternate code, every subfield subcode is an alternate code. We have some guarantees for the rate and the minimum distance. And this is one way to construct a good code, reasonably good code on over finite fields. Right now, so far, this is the best way of constructing good codes over finite fields. But asymptotically, so now suppose I want n to be large, d also to scale with n, right? And right, so d should scale with n, maybe linear in n, and but fp is fixed, say binary. Okay, then this doesn't give me a good approach. So if n grows with n, if n grows to infinity, then I need to make sure that 2 to the m or p to the m should also be larger than n, right? So m should scale appropriately, correct? But then if m also has to scale with n, then it means that this factor over here, d minus 1 times m, also has to scale with n. Potentially this could be much smaller. So high dimension. So really this factor is going to kill the original ring. Let's look at for p fixed, n growing to infinity. I want, let's say, d equal to delta times n. I don't care what delta is. It could be an arbitrarily small number greater than 0, but it's constant times n. Right? What happens? So k prime is the best that I can guarantee is that this is greater than or equal to n minus delta n minus 1 times m, correct? But now if I want n to tend to infinity, what should happen to m? M should grow at least logarithmically in, right? So k prime is greater than or equal to n minus delta n minus 1 times whatever log n, some constant times. But now this is linear in n. This is super linear in n. This grows faster than n. So which means that k prime just tends to 0 as n tends to. So this lower bound tends to 0. Anyway, this has to be at least 0. Negative does not give us any useful bound. So this approach is okay, but it doesn't yield us any efficient, asymptotically good code. The question is it at all possible to construct asymptotically good codes over small field sizes? So we know how to construct asymptotically good codes for large field sizes, Reed-Solomon codes. If Q is also allowed, or P is also allowed to grow with N, then we're fine. But otherwise, currently we don't know of any good way. That brings us to a new class of codes, again polynomial based codes, but which can be constructed over small field sizes. So these are the class of Reed-Muller codes. And they're going to use similar ideas to what we've seen so far. So how did we interpret Reed-Solomon codes? So one way of thinking about them is that, so generalized Reed-Solomon code is obtained by you take a polynomial and then you evaluate the polynomial at n different points. The reason why this didn't work for small field sizes is that you had to evaluate them at n distinct points. And now if you want n distinct points, then your field has to have sufficient. But now instead of looking at polynomials over one variable, what if I instead look at polynomials over m variables where m can be large? Does this get us something better? Is it possible to do something similar to Reed-Solomon codes? But now I look at multivariate polynomials instead of univariate polynomials. Yeah, p of x comma y, p of x1, x2, x3. So it's a polynomial in m different variables. And that is precisely the class of Reed-Muller code. Instead of evaluating at, so again, I need multiple points to evaluate, distinct points to evaluate particular polynomial. So now if I take a multivariate polynomial, then I get more points, more than p points. So again, we start with some field p. So now what does a multivariate polynomial look like? So multivariate polynomial is something which form m. So you have some coefficient x 1 raised to 1, 2 raised to x. So now this is a function of x1, x2, x3. So simple example, you just look at 2x1 2 plus x2 cube plus x1 square plus x1 square. This is a polynomial in two variables. It's a multivariate polynomial in two, right? So we need some notation over here. So we'll say that for this polynomial, the degree of this particular polynomial is the maximum sum of degrees of any monomial. Right? So in this particular example, the maximum degree is 3, or also 2 plus 1, 3. Add this plus x1 square, x2 square. The degree of this polynomial would be 4, because I have an element which is x1 square, x2 plus 2 is equal to 4. Sorry? Yeah, they're natural numbers. Yeah, whole numbers. That's always true for any polynomial. Okay. So the degree of m is basically the max overall 1 plus m. The coefficient should be. So for example, I look at what is the degree of this particular polynomial? 5, right? And the max, if you look at the individual degrees, that is degree with respect to x1, x2, and so on, then the individual degree of x1 is, the max individual degree of x1 is 3. The max individual degree of x2 is 4. So you can sort of distinguish between the total degree of the polynomial and the individual degrees corresponding to the variables. So in this particular example, the individual degree of 1 is 3, individual degree polynomial with respect to x2 is, but the total degree f of x is equal, right? Any questions so far? So now, how do you construct the class of Reed-Muller codes? So the Reed-Muller codes are specified by certain parameters. So firstly, you need the field size, which is, we'll assume, is Q, and an M corresponds to the degree, the polynomial that we will evaluate with respect. Sorry, M is going to be the number of variables. So it's going to be we are going to look at multivariate polynomials with M different variables, x1, x2 up to M, and R, which is going to determine the degree, max degree. The max total degree. So Q is the field size, M is number of variables, and R is going to be the max total degree. Okay? But so far I have not specified any polynomial. In fact, I'm not going to specify any polynomial. So the Reed-Muller code is obtained by taking the evaluation of all possible polynomials of max degree at most R at all possible values of the variables. Variables are picked from. So this is, so therefore the code words evaluations of all polynomials of max degree at most R, the individual degrees should be less than or equal to Q minus 1. There's a reason over here. And you're evaluating this at all points fq to the every variable, take all possible values basically. So what is n in this case? So it's not for any arbitrary n, right? So a particular code word is obtained by taking one polynomial, which is, let's say, a message polynomial, and evaluating at all possible points, right? So n, what should n be? How many points are you evaluating at? There are m variables. Yes. No, max degree is less than or equal to R. So you pick one particular polynomial. How many points are you evaluating this at? How many points are there in this? Q power n. So you're evaluating a given polynomial, a single message obtained by evaluating, taking one polynomial and evaluating it at all possible q to the m points. So n, the block length, is exactly equal to q to the power. Okay. The dimension, of course. So now what? How many code words are there? So looking at all possible polynomials, multivariate polynomials, max degree R, less than or equal to R, because the coefficient of the highest degree, highest monomial could be 0. Max degree should be less than or equal to. Can you give me any loose upper? In fact, computing this exactly is hard. You can't get a closed form in general. In general, no. Remember, there are a bunch of constraints, right? We'll see this, but fine. Okay, so let's maybe go to that later. Let's first take an example just to keep things concrete. Okay. Let us take R be equal to 1, Q to be equal to 2, and M to be equal to 2. What are all the polynomials that we have? So, two variables, degree at most 1. Yeah. Be less than or equal to. So this is a polynomial. This is a polynomial. The polynomial. The polynomial. What more? What more? Right? So how many polynomials are there? 8 possible polynomials. Right? And now I want to evaluate this for all possible pairs. How many points am I evaluating it at? So I'm evaluating it at 0, 0, 0, 1, 1, 0, and 1. x1 equal to 0, x2 equal to 0, x1 equal to 0, x2 equal to 1. So let's assume that I'm going to evaluate it exactly in this particular order. Okay. So, okay, what will the first code word be? It is the evaluation of this particular polynomial, right? So the first code word in the code book is evaluation of this polynomial at each of these points. What will that be? What is evaluation of this at this point? Evaluation of this at this point. Similarly, evaluation of this particular code word at each of these points, the constant polynomial. So no matter where I evaluate it, it's always the. So now let's take the third polynomial. So evaluate this at 0, 0. What is it equal to? 0, 0, 0. Wait. So this is the 0 polynomial, this is the 1 polynomial, this is the x1 polynomial. What about x2? Zero, 0, 1. So this is x2. So at this point it is equal to 1. x1, x2. X2 equal to 1. this is x1 equal to 1 and x2 equal to 0. Therefore, it's equal to 0. This is okay. Now, next polynomial is x1 plus x2. 0. What is the next polynomial? It is 1 plus x1. One, 0. Uh, wait, 1 plus 1. There's no only x1 is 1, 1, 0. Third is 1 plus 2. Last is 1 plus 2. 1 is correct. So this is a construction of the Reed-Muller code of max degree 1 binary and two variables. Now it turns out that in finding out the number of code words, getting the exact number of code words in general is very hard. Depending on, in certain regimes, you can easier to get a closed form, but otherwise it's not straightforward. And why is that? What is the number of code words equal to? So basically you need to count the number of possible polynomials whose maximum number of possible m variable polynomials whose maximum degree is less than or equal to r and individual degree is less than or equal to q minus 1. Right? So it's a counting problem, but in general it may or may not be an easy counting problem to get a nice closed form. For in the case where r is less than q, max degree is less than the field size, then we can get a nice expression. If is q, then the claim is that the dimension of the code is exactly equal to r m. This is the dimension of the code. This is the dimension of the Reed-Muller code. Exactly equal to r plus m choose. Yeah. No, that cannot happen, right? Which, yeah, correct. Correct. So the individual degree should be, if R is less than Q, then the individual degree should also be less than or equal to R. But then, yeah, so no. So individual degrees need not be equal to Q minus 1. That cannot happen, right? If R is less than Q, or if R is strictly less than Q minus 1, then the individual degrees can never be equal to Q minus. Maximum value they can take is equal to R. But then if R is greater than Q, then the individual degrees must be less than or equal to Q. And the reason why this is true is because or that restriction x to the Q minus, that it can that the individual degree should be at most to the Q minus 1 is because of the following fact. So in any field, FQ, x to the Q is equal. So if you look at a polynomial, if you look at the monomial and raise it to the power Q, then it is equal to 1. So it makes no sense to look at monomials of degree greater than Q minus. And this is true because no matter which, so alpha to the Q equal to 1 for all alpha. So let's stop here. For every alpha, no matter which element you take from the field, over FQ, any alpha from FQ, and raise it to the power Q, will always get 1. Okay, stop here. So for Reed-Solomon codes, a good reference is the book by Ron Roth. Textbook. For Reed-Muller codes, I'm following the notes by Atri Rudra, Jason Guru. Essential coding theory. So aiming to improve upon, in the sense, so a lot of new properties are being proved about Reed-Muller codes. So Reed-Muller codes are essentially algebraic in nature. Their distance properties are kind of well studied. But the recent results have been to show that Reed-Muller codes can in fact achieve the capacity of certain channels. In particular, Reed-Muller codes achieve the capacity of the binary erasure channel. That was proved like 3-4 years ago. That recent. Reed-Solomon codes, there was some recent work on list decoding Reed-Solomon. Different on how to efficiently list decode Reed-Solomon. But that was a while back, 2000s, early 2000s. On Reed-Muller codes, yeah, the latest work is because people have shown that Reed-Muller codes achieve the capacity of the PEC, and the conjecture is that they can also achieve, again, this is under maximum likelihood. They can also achieve the capacity of any binary input an output symmetric channel. So some classes of channels people have proved that they indeed achieve capacity, but in general, so in fact there are generalizations of Reed-Muller codes which are also known to achieve capacity of DEC. In fact, Dr. Lakshmi Prasad also had a recent result in proving that one particular generalization of Reed-Muller achieves the capacity of the binary erasure channel specific.